So far we've made analogies between linear motion and angular motion with regard to the kinematic quantities. So in linear motion, obviously we've talked about position. To a certain extent in angular motion, we can make an analogy between position and angle, or theta. I'll put a little warning here, which is that this does not actually behave particularly nicely once you get out of 2 dimensions, so that this analogy is one that you actually is problematic as soon as you move to 3-dimensional motion, which is why generally 3-dimensional rotation is a whole lot more painful to deal with than 2-dimensional rotation. But we've got this analogy between position and angle. We've got a stronger analogy between velocity and angular velocity. And the reason that we have a stronger analogy here is the sort of idea that it makes sense to define a velocity vector. It makes sense to define an angular velocity vector. The angular velocity has to do with the time derivative of the angular position. Velocity vector is the time derivative of the position vector, and so on. And we've also made this analogy between acceleration and angular acceleration. Now, where we're going next is making another set of analogies, and the next 2 analogies that we want to make are analogies between momentum and angular momentum, and force and torque. And of course, the reason that we want to be able to do this is that ultimately we're interested in finding equations of motion that describe not only how things translate, which is what F equals dp by dt tells us, but also how things rotate. In order to talk about how things rotate, we need to know what the sort of conservation laws are that describe rotation, as well as conservation laws that describe translation. Okay? So for translation, right, the fundamental sort of conservation law that we end up dealing with is the idea that the time rate of change of the momentum of a system is the sum of what the forces are on the system. And similarly for rotation, for rotational motion, what we're going to be interested in looking at is how the time rate of change of the angular momentum is the sum of the torques on the system. Now, I'll make a comment here that this sort of framing as talking about this as being purely about translation and this as being purely about rotation really is a little bit simplistic, to the extent that, in fact, when you start to look at, say, what the angular momentum of a particle is, you can actually, you don't think about that as purely being rotation, but it still makes sense to talk about conservation of angular momentum of a particle. So I would put a warning here that don't think about this right-hand side as being just about rotation. What it's really about is about 2 sort of fundamental physical quantities, angular momentum and linear momentum. And both of those are conserved quantities, and both of them have sort of governing equations that describe the flow of those quantities into or out of a system. That's a much more appropriate way to think about this than just thinking about this side as being the rotation side and this side as being the translation side. So with that caveat in mind, let's move on to start talking about angular momentum. And I'm going to start talking about angular momentum purely from a definitional perspective. And to get at the definition of angular momentum, let's actually remind ourselves what the definition of linear momentum is. So the definition of linear momentum for a single particle, so if I do linear momentum, for a single particle, it's just the mass times the velocity of the particle. For multiple particles, the angular momentum of a system is the sum of the masses of each particle in the system times the velocity of each particle in the system. Okay? And it makes sense with linear momentum to draw a system boundary and say the total angular linear momentum of the system is just all of the momenta of the constituent parts of the system. By the same token, for angular momentum, we can do the same thing. We have a definition for a particle, right? The angular momentum of a particle is the position vector of the particle crossed with its linear momentum. And by the same token, the angular momentum of a system is the sum of the position vectors of every particle in the system crossed with the momentum of every particle in the system. Okay? And just like in linear momentum, it makes sense to talk about the total linear momentum of the system. It makes equal amounts of sense to talk about the total angular momentum of the system. Let's do one quick example of that I think will highlight a couple of things. So I want to think about a sort of simple system where I have a sort of diatomic. I'm going to think about this as a diatomic molecule. So it's basically two masses. They're at the opposite ends of a dumbbell, and they're rotating about the xy axis, or xy about the z-axis, so they're rotating in the xy plane. There's this angle theta that describes what the angle is. And I'd like to know what's the angular momentum of this system. Well, let's say it's rotating at some constant angular velocity. So it's got some constant angular velocity, omega. Okay, so if I think about this point in the system, and let's say each of these are mass m, so this first mass, right, has a velocity that is in this direction, right? It's in the theta hat direction. The magnitude of that velocity is simply going to be, if this distance is r, it's going to be r times omega in the theta hat direction at that point. And if I take the vector r, so r for that first mass is going to be r times r hat. The momentum for that first mass is going to be m times r times omega in the theta hat direction. So the angular momentum of this particle for this particular case is going to be r times r hat crossed with m times r times omega times theta hat. R hat crossed into theta hat, r hat crossed into the theta hat is k hat coming out of the page. So I'm going to get m times r squared times omega in the k hat direction. Okay? So that's the angular momentum of this first particle. So I'll say for 1, 1, 1 for that first particle. For the second particle, let's think about this one. Well, the position of the second one, actually I could call this theta 2, right? So the position of the second one is also r, but it's times r2 hat, right? The momentum of it is going to be m times r times omega times theta 2 hat, right? And so L2 will be r times r2 hat crossed with m r omega times theta 2 hat. Well, let's see, what's r2 hat cross theta 2 hat? Well, r2 is in this direction. Theta 2 hat is in that direction. This crossed into this is coming out of the page again. So that also is going to be m times r squared times omega in the k hat direction. So the angular momentum of this system will be 2 times m times r squared times omega in the k hat direction. Okay?